This is the statement of the Leibniz theorem. You already know it. We have an alternating series. So this is a special theorem, and for a special case, and the case is for the alternating series where you have plus minus signs for each of the term. However, UIs are positive, and we say that this is going to be convergent if it satisfies the three conditions, and they are UN should be positive for the tail, UN should be greater than equal to UN plus 1. That means sequence should be decreasing. And if you take limit n tends to infinity, UN should be equal to 0. So these are the things which we have already know, right? We have done the questions on this. So we'll do the proof of this, that this is going to be convergent. And before going to the proof, you keep in mind that each and every condition is very important, and we're going to use it in the proof before, without even one condition, proof will not hold. Okay, so things will work only if we are using every part of this theorem. So let's say this. So what I'm doing is, so we know that if I want to write it as, so Sn, right? So that would be what? That would be, say, it is minus 1 raised to power n plus 1, u, say k runs from 1 to n, right? So if I take the partial sum of n terms of this series, which is given to us, this can be written in this way, right? So in other words, your Sn would be u1 minus u2 plus u3 minus u4. Last time we'll have un minus 1 raised to power n plus un minus 1 raised to power n plus 1. Is it okay? Is it okay?
Yes, sir.
So if you don't know, I'm repeating the things. You will start from un, so you'll have a positive sign. That means minus 1 raised to power 2. You start from u2, so you have u2, you have minus 1 raised to power 3. So you have one more power of minus 1, and then the index of this term, right? So when you reach at un minus 1, you will have one more power, that means minus 1 raised to power n. And when you finally reach at un, you don't know what is the value of n. So you simply write it as minus 1 raised to power n plus 1. Why? Because this depends on the nature of the n. If n is odd, then it will become positive. If n is even, then it will become negative. Why? Because we have one more index. If you have n to be positive, sorry, n to be even, then n plus 1 would be odd. So it will be a negative sign. Is it okay?
So why did you took that n plus 1 in last?
That's what I'm saying. See, when you have u1, you have minus 1 raised to power 2.
Yes, sir.
When you have u2, you will have minus 1 raised to power 3. That's why you got that negative sign.
Yes, sir.
So whatever the term is, it will be multiplied by one more the index of minus 1 raised to power 1 more the index of that term. That's why I've written the n plus 1. Right? Is it okay? Okay. So let's see.
Sir?
Yes?
Sir, Sn would be summation minus 1 to power k plus 1 uk.
I need to change the a bit notation over here. That's it. Okay. So is it fine now?
Yes, sir.
Okay. So let's move. So let's move how the things will work. So suppose I'm taking a specific case. So I'm putting n is equal to 2m. So that means I'm taking even many terms, right? So how it will work? So you will say S2m. So it would be u1 minus u2. Then you have u3 minus u4. Then you have u5 minus u6, and so on. You know that you want to go to the 2m terms. So the previous term to the um term would be what? Just previous one, u2m minus 1 and minus u2m. Why minus u2m? Can anybody tell? Can anybody tell?
Taking the next
sign, so it will be negative.
Yes. Because we'll be multiplying by minus 1 raised to one more power that of the term, that of the index of the term. And index of the term is already even. So we are sure that the power of minus 1 would be odd. So that's why this term will be a negative sign. Similarly, the previous term to u2m, which is u2m minus 1, will be a positive sign. Okay?
Yes,
Okay.
sir.
So,
Yes,
so
sir.
now, if I suppose I want to write it S2m plus 2, right? Let's say I write it S2m plus 2. How are we going to write it? U1 minus U2 plus U2 minus U3 minus U4 plus we go like this and U2m minus 1 minus U2m plus trying to say is you're going to understand this. Let me pick this thing. Let me pick this thing to the next page so that you can actually understand. Let me pick this whole thing to the next page. Okay. So this is not going to be covered over here. And let's make some space over here as well. Okay. So now it becomes U2m plus 1 minus U2m plus 2. Now is it fine? Is it okay?
Yes, sir.
Since UI is decreasing, why it is decreasing? Because it is given to us that your UI is decreasing, right? This is given to us by second.
Yes, sir.
By second. Okay. So if it is decreasing, you know that each bracket is positive, each bracket is negative or positive. U1 is greater than
Positive.
each
Sir,
bracket
positive.
positive. Each bracket is positive, right?
Yes, sir.
So now you know that if you check these brackets, it's fine, but S2m plus 2 has extra bracket over here, right? So S2m plus 2 is
Great.
greater than equal to S2m. Is it okay now?
Yes,
Yes,
sir.
sir.
Is it okay now?
Yes, sir.
Is it a nice? So now rewrite the expression of U2m, sorry, S2m. Rewrite. So how are we going to rewrite? So let's say, so this is your S2m, right? So now
Yes,
your
sir.
S2m can be written as in the same way that you will write U1 here minus U2 minus U3. Then minus again U4 minus U5. Can I rewrite in this way?
Yes, sir.
Minus and so on minus, and last time I would like to write it as U2m minus 2 minus U2m minus 1 minus U2m. Is it okay now?
Yes, sir.
Yes, sir.
Is it fine? So now you
Yes,
can
sir.
tell me, can each bracket is positive or negative? What about each bracket? Is it
Positive.
positive?
Positive.
Positive.
This is positive, but this negative is already over there. And this
Yes,
is
sir.
also positive, but this negative is over there. So if you talk about this quantity is negative.
Yes, sir.
Yes,
So
sir.
basically you are subtracting something from U1.
Yes, sir.
Right? So this quantity will be always
Negative.
less than or equal to U1. True? Is it
Yes,
fine?
Sir.
Yes,
So what do you
sir.
get? So what do you get? So I'll mark this thing as star and this thing as double star. So your S2m is less than equal to U1. Is it okay?
Yes, sir.
So from here, your S2m was increasing. So from star and double star, S2m is increasing and bounded above by U1. True?
Yes, sir.
Yes, sir.
It's true.
So
Yes, sir.
if your sequence is increasing and it is bounded above by a number U1, then it has to be
Convergent.
Convergent.
Virgin.
right. So therefore, S2m is convergent, and let's say its limit is L. Let's say its limit is what? L.
L.
So that means limit m tends to infinity, s to m is equal to L. Right? Now, this is something which you have done only for the even part. Let's say if your n is odd. Let's say if you consider s to m plus 1. Right? So consider s to m plus 1. So s to m plus 1 would be what? It is nothing but partial sum s to m. You just add the next term, that is what? U to m plus 1. Is it okay?
Yes, sir.
Is it okay?
Yes, sir.
Yes, sir.
Are you okay with this? Right?
Yes, sir.
Yes.
You know ना कि अगला पार्शियल सम निकालना हो तो क्या करते हैं? कुछ नहीं करते हैं, पिछले पार्शियल सम में अगली टर्म ऐड कर देते हैं. यही होता है ना?
Yes,
So
sir.
now,
Yes, sir.
so now if you take limit n tends to infinity s to m plus 1. So now you take limit n tends to infinity s to m plus limit n tends to infinity m tends to infinity. I would write this u to m plus 1. Okay, so this thing was what?
L.
L. And what about this thing? Can anybody tell? Anybody?
Zero.
Yes. Kyun zero?
Approaching to zero.
Because they are decreasing.
Yeah. No. Anything? See, every decreasing sequence may not be zero. Decrease कर रही है तो 1 तक भी decrease कर सकती है ना? अरे, just because we have given this.
Condition है sir.
Yes. Right?
Yes, sir.
Yes, sir.
So this is going to be 0. By what? By part 3. Right. So from here we can conclude that limit m tends to infinity s to m plus 1 is also equal to L. ठीक है. अब हमारे पास we used to have a theorem in 8.1 exercise 53 है. You're gonna check that. In that we have mentioned that a sequence is convergent if its even subsequence and its odd subsequence converges to the same limit, right? So by that result, which you don't need to prove that result, okay? You just directly use it. So since your limit m tends to infinity s to m plus 1 is L, and your limit m tends to infinity s to m is also L, therefore limit m tends to infinity sm is also L. And what is sm? This is the sequence of partial sums, right? So therefore our original series m runs from 1 to infinity minus 1 raised to power m plus 1, doesn't matter if you change the index from m to n, doesn't matter, um is also what? Convergent. Okay, now you see this, we have used every part, right? So you check this, we have used the part 2 as well, right? And we have used this part as well, and we have used this part as well. Are you with me on this?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
समझ आ रहा है?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, you got it? So should we move further?
Yes, sir.
Yes, sir.
Yes, sir.
Sir.
Okay,
Sir, I
good.
have a doubt.
Yes, please.
So can you switch to the previous slide once?
Yes,
Sir, the previous one. One minute.
yes.
Sir, in this, how is S2M increasing? Sir, it should be decreasing.
No. You see this? I just wanna. I'm not taking this S2M from here. From here, I'm only proving that your S2M is bounded. Bounded above YU1. Now you see this over here. Now, can you check the brackets?
Yes.
Since your U1 is bigger than U2, why your U1 is bigger than U2? Because it is given that our UIs are decreasing, right?
Yes.
So your
Yes,
first
sir.
bracket is positive. Your every bracket is positive.
Yes, sir.
So up to this stage, this is same. S2M plus 1 and S2M is same.
Yes.
But S2M plus 2 have an extra factor of this.
Yes, sir.
This is also positive.
Yes.
So we are adding something to S2M plus 2 over S2M.
Yes.
So S2M plus 2 has to be bigger than or equal to S2M.
S2M. Yes, sir. I got that.
Okay.
So,
So
but
anything you
how
want to
does
ask? Yes,
so, but
yes,
how
yes.
does this prove that S2M is increasing? Because S2M should be decreasing as U1 is the upper limit, upper
No, no,
bound.
no. Yeah, but that it should not decrease. See, if somebody is if something is increasing, you have a bound from above that actually guarantees you it will cluster somewhere, right? So if something is decreasing, you need a bounded below in order to prove that there is some convergence.
Yes.
Okay. So
Okay,
if it
sir.
is something increasing, it should not be bounded below. We don't have anything to do with that, right?
Okay, sir.
Are you getting me this? Are you getting?
Yes, sir. Yes, sir.
Everything is fine?
Yes, sir.
Now, अच्छा, अब कल हमने किया था absolute convergence, conditional convergence, or simple convergence. So I want you to restate the facts. Can you tell me what is the difference between these things? What is absolute convergence? What is convergence? What is conditional convergence?
So
Sir,
absolute
conditional
means if the
convergence,
modulus is convergent.
हाँ,
if the
ठीक है.
modulus is not convergent, then it
Then it is
becomes
conditionally
Conditionally
convergent.
convergent.
No.
convergent.
You should say this. If your modulus series is convergent, but your modulus is not convergent, but your simple has to be convergent. Only
Yes.
then you
Yes,
will
sir.
say that it is conditional convergence.
Conditional.
ऐसा
Yes.
नहीं होना कि series खुद ही divergent हो जाए. So how you can say that कि then it is conditionally convergent?
Yes, sir.
Yes, sir.
Now this is an important result which I'm gonna prove. This is the part of the part of our syllabus now. So this can be asked. It's a very simple proof, and I'm giving you a very important results today, which you must observe. Okay. So what is that thing? So that is our theorem. Theorem says what? Our theorem says that if summation n runs from 1 to infinity mod an is converges, then summation n runs from 1 to infinity an is also convergent. मतलब once absolute convergent, you don't need to prove the convergence. कल मैं क्या कह रहा था? Yesterday I was saying that in order to prove that it is absolutely convergent, you need to go two things. What are those two things? First, you need to check the convergence. Then you need to check the absolute convergence. Then you say that absolute convergent is there. Okay? But now today I'm proving a stronger result. I'm saying that if you only prove this is convergent, so you don't need to prove the regular convergence. That is always there. Okay?
Yes, sir.
Right?
Yes, sir.
चलो, ये तो है ही है ना कि कोई भी term will be lesser than or equal to its modulus and will be greater than equal to minus time of its modulus. Every number satisfies this inequality, right?
Yes, sir.
Yes,
Okay.
sir.
Okay, so if I add these things, add mod of summation n to both sides to this entire inequality, can I write in this way? Okay.
Yes, sir.
Now you think this is an and think this is bn, right? Now summation mod an is convergent. Why? Why?
It's because
It's
2
given.
Given है, ठीक है. So 2 times summation mod n is also convergent, right? So if you consider this star, so and you think this is a kind of comparison test, so if this is convergent, so this part is also convergent, right? Series
Yes,
of this
sir.
part.
Yes, sir.
Yes, sir.
So therefore by comparison test, an plus mod an is also convergent, right? सही बात है?
Yes,
So
sir.
therefore summation an plus mod an minus summation mod an is also convergent? Is it true? Is it true? Is it true?
Yes, sir. Yes, sir.
Why? Why?
Convergent minus convergent is
Convergent.
convergent only.
Of course, difference of two convergent series. Hana, we have already proved that this is convergent. We have already proved by comparison test. This is given, right? That this is convergent. So difference of these two will of course be convergent. Okay. So that means now what is the difference? Difference is you'll cancel mod n and therefore is convergent. Right?
Yes, sir.
समझ आया?
Sir, please switch to the previous slide.
Yes, yes. Okay.
Yes, sir.
So what I'm saying is, now keep in mind, what I'm saying is absolute convergence implies simple convergence. Right? In series, keep in mind, in series, not in sequence. I'm talking about series. Okay? But are you getting this? Are
Yes,
you with
sir.
me? So,
Yes, sir.
but convergence does not imply absolute convergence. Are you getting this?
Yes, sir.
Again, I'm talking about zero.
Yes, sir.
So, can you give me an example where convergence doesn't imply absolute convergence? Yes, we can have an example of conditional convergence. For example, we have this thing. This is convergent, right? But not absolutely convergent. Can you prove this? How are you gonna prove that this is
Yes, sir.
convergent? Yes, sir. How are you gonna prove that this is convergent?
Leibniz theorem.
Exactly. Leibniz theorem से. And how are you gonna prove that कि ये absolute convergence नहीं है?
Modulus.
फिर उसके बाद
P test से.
P-test.
Yes, sir.
P-test,
P-test.
yes,
And after
sir.
that, retest.
Yes, you're gonna prove it by P test.
P-test.
Right?
Sir, can you please switch to the previous page?
Yes. Right? So once you prove the absolute convergence, you directly go to the absolute convergence. That's it. Okay?
Yes, sir.
Okay?
Yes,
True?
sir.
Okay, so let's do a few more questions. We'll include few more questions on that, and we'll have only, one more lecture. We'll spend one more lecture on this, and we'll do the error part, that how to approximate the error. So that is something which is different. We're going to do it tomorrow, but we'll do this, kind of same questions on this. So let me check few questions for you. Yeah. So let's say question number 22. Okay. So let's try to prove that this is absolutely convergent. We need to check that. So question is, summation n runs from 1 to infinity minus 2 raised to power n plus 1 upon n plus 5n. Okay, right? So consider the absolute values. So how are you gonna check it? So once you implement the absolute values, you are no longer eligible to apply the Leibniz test. Okay, because Leibniz test is made only for the alternating series. So this is 2n plus 1 upon n plus 5n. So can you think of any test which we can be implemented here? Comparison test, ratio test, root test. Which kind of test you want to implement over here?
The ratio test.
Ratio test.
Ratio
an
test.
plus 1 by
Ratio.
n.
थोड़ा सा comparison के बारे में भी सोचो. Comparison is pretty much easy to write.
Yes sir, comparison से हो जाएगा.
Removing n from denominator.
Can I write it in this way?
Yes sir.
Yes, sir.
Why?
Yes, sir.
Because we have removed that n. Now the things
Yes,
become
sir.
little bigger.
Yes,
so this
sir.
can be written as 2n by 5n.
Oh.
Yes, sir.
So
Yes
2
sir.
times
It
the-
will become GP.
It will become a GP,
Yes.
sir.
Yes.
Yes sir.
It will become a GP.
Yes, sir.
Yes, sir.
So this series will be convergent by comparison test. This is convergent. Is convergent.
Yes, sir.
So this will also be convergent.
Yes, sir.
Right?
Yes, sir.
Yes
So
sir.
therefore, summation 2n plus 1 n plus 5n is also convergent. And what we gonna say to the our original series? Our original series will be what? What? Absolutely convergent. Not convergent. Absolutely convergent. Why? Because its mod is convergent. Okay. And we have done the result that if something is absolutely convergent, then it is convergent. Okay. In series. Okay. So in series, if it is absolutely convergent, therefore it is convergent. You don't need to prove the convergence explicitly. Okay.
Yes, sir.
So please show the previous slide.
Yes.
Excuse me, sir.
Yes.
So means अगर हमने mod से convergence proof की तो absolutely convergent भी हुआ और convergent भी हुआ.
Yes. Because absolute convergence is a stronger thing. हमने यही prove किया ना, because if you have absolute convergence, it is already inheritedly convergence. We have proved the fact by using this theorem. Okay.
So तो जो हमने कल की थी वो क्या कहती है?
हमने कल कोई थ्योरम करी ही नहीं.
Absolute वाली.
हाँ, कुछ नहीं किया. कल हमने डेफिनेशन करी थी सिर्फ. Okay.
Okay, sir.
कल हमने अलग अलग प्रूव किए थे, no doubt, but I'm saying that today we are going to prove a stronger result.
Okay, sir.
Right. So now from here onwards, if you get the absolute convergence, you don't need to prove the convergence separately. Okay. But if it is convergent, then you are not sure that it is going to be absolute convergence or not. And if in case if it is not absolute convergent, we'll call it only conditionally convergent. Right.
So means अगर mod से आया आंसर divergent आता है तो हम कहेंगे conditionally convergent.
नहीं, तब हम ओरिजिनल कन्वर्जेंस चेक करेंगे और अगर वो ओरिजिनली कन्वर्जेंट हुआ तब क्या बोलेंगे? कंडीशनली कन्वर्जेंट है. और अगर वो ना हुआ तो डाइवर्जेंट ही हुआ ना. कंडीशनली कन्वर्जेंट नहीं बोल पाएंगे फिर.
Okay, sir. Means mod के साथ-साथ उसका originally convergence भी चेक करना होगा.
See, if you check the mod convergence, if it is convergence, then it is convergent. Okay, let me construct a table for you. Say if this is convergent, so what does that mean?
Absolutely convergent.
Your original AN is absolutely convergent. And since your absolute convergence implies the convergence, and regularly भी वो क्या है? Convergent. But if it is divergent, then what are you gonna do? Then you're gonna check. If then regular is, then of course it is not absolutely convergent. Absolutely convergent nahi hai. That's what I'm saying over here. So yeah. So if this is not, if it is divergent, then you're gonna check. हम इसे अब absolutely convergence तो नहीं कह सकते. But if your summation AN is convergent, then what are we gonna say? Then summation AN is what? Conditionally convergent. Okay?
Okay.
और ये भी हो सकता है, और summation an may come out to be divergent. हो सकता है divergent ही आ जाए, है ना?
Yes, sir.
So if you are absolutely convergent, if you are able to prove that it is absolutely convergent, then you are the luckiest person on the earth. You know that if it is absolutely convergent, then everything is convergent, then fine. But if you are able to prove that it is divergent, then you cannot say anything. You will simply say that it is not absolutely convergent. Yes. Further, if this comes out to be convergent, then you will say that it is conditionally convergent. Okay. Or it may come out to be that it is even not conditionally convergent, it is divergent. Right?
So फिर अगर a n divergent है फिर हम क्या last
कुछ
हमारा?
नहीं, आ गया divergent तो आ गया.
Okay, sir. So means finally divergent.
Oh, of course. Okay.
Oh.
So अगर आ ही गया divergent, you don't need to say anything. You'll conclude that this is divergent. Right? So that's
Okay,
it for
sir.
today. If you want to ask some doubt, you may ask it. For learning purpose, you may revise today's lecture. Otherwise, it's fine. You got everything?
Yes, sir. Yes, sir.
एक्सक्यूज मी सर,
Yes.
सर जो हमने कल एग्जांपल किया था उसमें एब्सोल्युटली तो कन्वर्जेंट आ रहा था, लेकिन बाय डायरेक्ट कंपैरिजन टेस्ट वो डाइवर्जेंट था.
कहाँ पे मेरे को बताओ. We'll come to that example.
-1 raised to the power n
ये वाला.
by log 1.
तो कहाँ पे आ रहा है? ये कहाँ पे आ रहा है बताओ. ये एब्सोल्युटली कन्वर्जेंट नहीं था ना, ये सिंपली कन्वर्जेंट था. एब्सोल्युटली डाइवर्जेंट था. आर यू गेटिंग दिस?
यस सर, यस.
एब्सोल्युटली तो ये डाइवर्जेंट था, एब्सोल्युटली कन्वर्जेंट नहीं है ये. तो ये फाइनली क्या बना था, इसीलिए कंडीशनली कन्वर्जेंट बना ना.
यस सर.
क्योंकि तुमने एब्सोल्यूट चेक किया. देखो, एब्सोल्यूट चेक किया, डाइवर्जेंट आया. फिर तुमने ओरिजिनल चेक किया तो कन्वर्जेंट आया. ठीक है, तो इसका मतलब ये क्या बना, कंडीशनली कन्वर्जेंट. एंड दैट्स व्हाट वी हैव कंक्लूडेड इन आवर नोट एज वेल. यू सी दैट इफ एब्सोल्युटली कन्वर्जेंट तो बाकी सारे तो उसके लिए. इफ इट इज सिंपली कन्वर्जेंट देन कंडीशनली. ये आया ना हमारा केस, दैट योर समेशन मोड n इज डाइवर्जेंट, सो इट इज नॉट एब्सोल्युटली कन्वर्जेंट. So your summation mode an is convergent. वो हमने प्रूव किया convergent है. That's why we concluded that your summation an is conditionally convergent. Okay.
Yes sir.